start. Welcome to the last section. My voice is low, sorry. Thank you for the last for coming to the last section of this day. And the first speaker is Tomoyuki Yamakami. And he speaks about structural complexity of multi-valued partial function computed by nondeterministic pushdown automata.
Thank you very much for the nice introduction. Well, today's my talk is about the structural complexity theory based on the finite automata theory. But before going to the main theme, I want to just give you some tips about the University of Perugia. I came from all over from Japan, so I want to give you some information about Japan, particularly the Fukui. Japan is composed of 47 regions. We call it the prefectures. And the prefecture is around here. Japan is consisted of 4 big main islands, and one of somewhat in the middle of this big main island. And the distance from Tokyo is around here, to Fukui is about 3 hours and 30 minutes by train. And Osaka and also Kyoto is much closer, just 1 hour and maybe 30-40 minutes by train. And Fukui prefecture is, the shape of the prefecture is look like the tadpole, the baby of frog, like a big head here and the tail is around here. In the Fukui city, the university is actually located in this city, the Fukui city. And the city is around this head of this tadpole. Okay, now we'll go back to the main theme. Today's talk is all about structural complexity in terms of about the multi-valued functions. I'm going to explain what the multi-valued function is. But then so I'm staying in the framework of formal language and automata theory. And I will investigate the characteristic features of the multi-valued partial functions. Particularly, I'm interested in CFL functions. CFL stands for the context-free languages. And I'm going to prove several interesting containments and separations among some newly defined function classes. So I start with the very basic motivational argument. I have been working on structural complexity theory within the framework of the formal languages in automata theory. And since 2004, so almost 10 years ago, I started introducing the concept like bias and immunity and dissectability and pseudo-random generator and CFL hierarchies. So today's work is the kind of continuation of those structural properties. And first of all, I'm going to discuss functions instead of languages. Why we need functions? Mostly people work on the language theory in the framework of automata theory. But if you look at it, natural problems, for example, search problems, or the counting problems, and optimization problems, those problems are actually requiring solutions. So you can, from a different point of view, those problems can be considered to be functions. So you have input and you have output. So it's very natural to think about functions instead of languages. Well, languages is considered to be kind of a special case of functions. Particularly functions outputting either 0 or 1. So another point is that well, we have plenty of nice works about multi-valued partial NP functions. NP function is the function computed by polynomial time non-deterministic Turing machines. So why don't you study the similar functions in terms of non-deterministic pushdown automata. So that's the motivation, and that's actually brought into this field. So before that, now just to give you just a brief sketches about what's happening in the polynomial time setting. We have a number of the very interesting complexity classes. NP-MV, so this is actually the class of functions, multi-valued partial functions computed by non-deterministic polynomial time Turing machines, NP machines, I just simply call them. Single-valued portion of the NP-MV is called an NP-SV. S stands for the single value. And if you just limit your attention to a total functions, then we just put the small letter t as a subscript. And the relationship among those complexity classes is actually categorized like this one, pictured like this one. So that the upper class contains the lower class. And those classes are actually separated by definition because the multi-valued function cannot be single-valued. But we don't know about the lower level here. This is actually polynomial time computable functions, and this is actually non-deterministic NP, SV with the total functions. But we don't know the separation between them. If you have a separation between them, so that actually implies that the P and NP are different. So you can actually award $1 million kind of. So I'm going to talk about the CFL functions, but the CFL functions are not really new, and that is actually all the languages. The Eggy and Fisher, they actually wrote a paper about the CFL function. They did not really call it the CFL functions, but those functions are also known as algebraic transactions. So those are very old, 1960s. Now we will focus on the CFL functions. So I'll just give you the definitions first. And everybody knows the Pushdown Automata. This is actually taught at the very first, well, probably in the second year of the computer science department. And we have stack here and then tape, input tape here, and assuming that the head only moves one direction. And the input string is actually surrounded by the two end markers. Now, to compute the functions, we just simply add extra tape, that is the output tape. And this tape is write only. That means that whenever you actually write a symbol, non-blank symbol, the head has to move to the new blank cell, so that the head doesn't read already written symbols again. So this is actually the picture what's happening in the computation level. So we start with input X, and this is a non-deterministic machine. So they actually have a number of non-deterministic computation paths. And eventually, they actually can output something on the output tape. But we actually put the conventional convention that whenever the path actually to reject it, that means going into the rejecting state, we simply disregard the outcome. So we only actually take the outcome that following along the accepting path. Those are actually called the valid outcomes. But we only deal with the valid outputs. So we don't need to talk about anything invalid outcomes. And sometimes we have that all computation paths terminate in the rejection state. That means the outcome of this machine is empty, right? That's why we call it a partial function, because then sometimes we don't have the outcome. And multi-valued, we call the function multi-valued because we could possibly have several, not a single, outcomes. And this is more often a formal definition of the machinery I just explained. But the most important thing is that we impose a termination condition. The termination condition said that in all computation paths, including accepting and rejecting all possible paths, all the paths have to terminate within the linear time in terms of the input sites. And this is actually not really strange because if you look at it in the language, right, the context-free languages, then you can always find the linear time non-deterministic pushdown automata. So this is just a simple extension of the language case. So now we will just give the definition of the multi-valued partial CFL functions. So those functions are actually computed by non-deterministic pushdown automata, and we will actually form the three major complexity classes: CFL MV, CFL SV, CFL SVT, similar to the MP case. CFL MV is the class of the multi-valued partial functions computed by the non-deterministic pushdown automata, and SV, if I write in SV, that stands for the single-valued portion of the CFL MV, and the small letter t stands for the total function. Then we have very nice separations of the complexity classes. The upper class properly contains the lower class. And the bottom case here, we have the separation here because, in the NP case, we never know whether an FP is equal to NP SVT, but then here in the automata theory, we can have an actual separation. So this separation is similar to the separation between regular languages and CFL in a language level. So I'll give you, if you're not familiar with this field, then I'll just give you some examples. The first example is the function called PAL, the palindrome. The W is an input. If W has, we will find a substring inside this W, which is the palindrome. So there could be several palindromes. This particular function is belonging to the CFL MVT, so T stands for the total function. Another one is the IP2. So the input is X, and then we'll find Z. The inner product between X and Z, mod 2, is going to be 1. So this particular function is actually CFL MV. But then if you just carefully look at it, and then you just find out that we don't need a stack. So actually this function belongs to the NFA-MV. So NFA-MV is the class of functions computed by the one-way non-deterministic finite automata without any stack. So now we'll look at the operation defined between the functions. Now we'll start with the conjunction. Conjunction, suppose that f and g, the capital letter f and g, are complexity classes, the complexity class of functions. And if you take the conjunction of two of the function classes, so that means we'll take suppose this is in a G1 and this is actually in G2, then we'll just take the intersection of the outcome of the two functions. And the disjunction of an f and g is exactly opposite. So just to take the union of the outcome of the two functions. That means the whole entire outcomes. And similarly, we can define the difference and the complement. The difference between the two function classes is actually defined by using the set difference. Remember that the function is actually producing a set of solutions, right? So we can actually take out the some portion out of the some set of solutions. And the complement, this is defined slightly artificial, but we will just take a look at the whole entire string of the length at most in a polynomial in the size of an input. And then, if G produces this portion of the solution, then we just take the rest to be the outcome of this F. So that's a complement. And we'll get the very nice properties. For example, that if you take a complement of complement, that goes back to the original one. And complement of the CFL-MV is actually characterized by the difference between the MFA, MV minus the CFL-MV. Right? So this is another way to define the complement. And CFL CFLMV minus CFLMV is exactly the same as in CFLMV conjunction of complement to the CFLMV and so on. The last one, so this actually says that the CFLMV is not closed under complementation. Now we're going to do the reduction. And the reduction is the way to actually to expand the complexity classes. That is often known to introduce a complete problem. For example, the NP complete problem. That is actually done by the reduction. So now we can think about the reduction between for the functions. So this is actually the non-deterministic Pushdown Automata standard model. Then we add extra query. So the machine can produce a string on this query tape. This is actually the write only, similar to the output tape. And whenever the machine actually make a decision to make a query, then the information written on this query tape is automatically transferred to the oracle, and the oracle make a decision, yes or no. And then all the information, the decision is transferred to the machine back again. So the minimum reduction is defined similar to the standard NP minimum reduction. We'll take the oracle NPDA, so that's the non-deterministic Pushdown Automata with the oracle tape. And this particular machinery taking input X and produce two things, and the Y and Z, and along the accepting computation path. And the outcome of this function is Z, provided that the Y actually belongs to A. So the oracle A actually says yes. So we just simply collect all possible Z's that corresponding to that yes answer. So we'll use notation like this one, similar to the NP hierarchy. And I'll just give you one example. For example, the Duke 2, that's the input is W, and then if W has XX in the form of X in X, then we just simply output X. If it doesn't, then we just simply output empty set. Right? This is not CFLMV. This function is much complex than CFLMV functions, but this is actually reducible to CFL language A. So an A has an X to the reverse and separator and X. So this is actually CFL language. And the algorithm of the reduction is something like this. And then I'll just show you in the picture. So first of all, take input W and split into X and Y in two portions. Suppose that we have W is 1, 0, 1, 0. Then we split into the first one, lambda and 1, 0, 1, 0, and 1 and 0, 1, 0, and so on. Then we just split in the first section, 0 section, first section, second section, and so on. And also, we just produce the produce the strings onto the output tape. Then we just make a query to the oracle A, and the oracle says in this particular case no, no. In this particular case, we have yes. So an oracle actually can make a decision yes or no, and that information are actually sent back to the finite automata. So the finite automata reject, and whenever the oracle answer is no, and then yes, accept, and whenever the oracle answer is yes. So the outcome is 1, 0, right? Now, so this query mechanism, oracle mechanism, is actually the non-adaptive. So now we introduce a different kind, an adaptive queries. So in this particular case, we start with the input X, and then follow the computation path. So whenever we produce a string on the query tape, we just make a query. And the oracle make a decision, and we receive that decision, and then just keep going on the computation. So we never stop for the first query. We just make a second query, third query, so on, up to the machine decide to stop, right? And then they actually can make a decision. So this is the adaptive queries. And using this particular adaptive queries, we can define the two-ring reduction instead of the minimum reduction. Well, standard NP completeness use the minimum reduction, but also Steve Cook has initially introduced the two-ring reduction to introduce the NP completeness, and later on the CART actually can make introduce the minimum reduction, so that the order of the reduction, minimum and the two-ring are actually opposite. But anyway, so we will just so similarly we defined the two-ring reduction, and we actually can ask the termination condition to be halt. Okay, and we'll introduce the CFL-MV hierarchy, so that the reduction actually make us possibly can build a hierarchy over the NPA CFL-MV. So that the CFL-MV hierarchy is defined the following way. So that the first level of CFL hierarchy is CFL-MV, and the second and third and fourth and so on. Those higher level of the hierarchy is the actually CFL-MV to the oracle pi CFL-K. The pi CFL-K is the kth level of the CFL hierarchy that is introduced in SOLSTEM this year. And similarly, we can actually define CFL SV hierarchy. And the hierarchy actually, the lower level complexity class is actually contained by the higher level hierarchies. So what we can do about all the functions in this CFL-MV hierarchy. So I'll just give some idea. So think about the following particular kind of functions. So you simply run the non-deterministic pushdown automata, and then take a look at all the valid outcomes. And then you just simply choose the optimal value, either the maximum or minimum, according to the dictionary order, not the lexicographic order, because of the statutes. But anyway, so this is actually an optimization problem. So we actually can optimize, find an optimal solution of this particular function. So we'll call it an opt CFL, because then we actually calculate the optimal value depending on the CFL framework. So this particular, for example, then we just go back to the PAL. So this is actually the function finding the substring that is a palindrome, right? And then we just simply output the maximum palindrome. Then this is actually a single valued function, and this belongs to the opt CFL. And
So you are entering in your question time.
oh, I see. Okay. Thank you. So the opt CFL is located between the CFL SVT and the fourth level of the CFL SV hierarchy. And this is quite different from the NP case. In the NP situation, the opt P that corresponds to the opt CFL is actually contained within the second level of the NP SVT. So we have a slightly different situation here. And also, we can actually show the separation between the CFL SVT and the opt CFL. So we don't know the same situation in the NP hierarchy. And but then if you just restrict the opt CFL slightly, then we can actually put this one inside the second level's hierarchy. And relationship between those things are actually described in the following way. So the CFL hierarchy, I just mentioned this one. So this is actually introduced in the SOLSTEM this year. And we have the relationship between the language hierarchy and the functional hierarchies. So we are actually dealing with the function complexity classes. So those complexity classes are all different by definitions. So it's no use of thinking about or discussing the content of the one complexity class to the other, right? So instead, we can actually think about refinement. This is actually the choice function. So if you have the set of solutions, we are actually picking out some elements from that solution set. So this is called the refinement. And we will use this notation to denote that all function in G can be refined by the function in F.
Just 2 minutes, really.
Okay, thank you. So the example is that the max power, that computing the maximum element in the substring that is palindrome. So this is actually picking up the one particular element in the power. So this is actually the refinement of the palindrome function. So there's a the separation among the CFLMB and CFLMSB in terms of the refinement that is actually presented in the TCS in Rome a few weeks ago. The theorem in this paper, in this talk, is if you have a collapse here, then we have actually the refinement contradicting this one here. But the k is bigger than 1. So now the future challenge. We want to prove the separation among the higher level of the hierarchy, and also we want to show that the refinement is impossible also in the higher level of the hierarchy. So thank you very much for listening, and now I'll take the question and answer. Maybe no question.
There is time just for one question, I think.
Okay.
But if you don't have any stack, you just the lower level, regular languages instead of contextual languages?
Well, still, you can actually introduce, as I said, you can introduce an NFAND. So that is actually the function class computed by the non-deterministic finite automata without any stack. But still, you can actually, prove very interesting properties.
Okay, I have also a super fast question. Just if in this complexity theory community there is some interest also for quantitative setting, which you have function not from string to string or string to set of string, but from string to a number, and then you compute, for example, the value of a run as the sum of the or the discounted sum, so on. So you can have also a quantitative reformulation of the refinement problem.
Well, in this particular talk, I'm just considering the function that actually mapping from string to string, not
so
the other way. So, but in the polynomial type setting, you can actually translate the string into the graph or table or whatever, right? But in the finite automata level, sometimes you can't change it.
Yeah,
so the interpretation might be really important.
Okay, so you interpret. Okay, thank you. Thanks, the speaker.
Okay, thank you very much.